applications for robotics, autonomous system, with reality, and so on. And there are many multiple challenges within dynamic scene understanding. But for this, we'll try and focus on first is the time-varying geometry, which is the things are constantly changing, constantly update, and then we focus on the motions of the entities within the scene. That is articulated motions of humans and robots and other entities as well. And we focus on the part-level understanding, and this is especially important for robotics applications, where we have to understand about the parts and the compositions of objects within a dynamic scene and how they behave. So, to start, what is 3D Gaussian splatting anyway? So, imagine now I have a bow. I can just simply record everyone within the frame, within this room, and somehow we can build a 3D model that can reconstruct and capture the dynamic scene, the dynamic nature of this room and the event within this room as well. And Gaussian splatting is like when we have an object, there are multiple smaller ellipsoids, smaller particles that are called Gaussians. Each Gaussian will act as a particle where you can view under different points. So the task is not simply just reconstruction, but it's also novel view synthesis, which just means that based on what we can observe, what we can learn, we can also infer how other views and how other views of a certain objects, of a certain scenes will behave by using a blending and using the Gaussian clusters to cluster with similar points. And it has shown very promising rendering effects with high real-time rendering quality while maintaining a very low train time with a very simple, straightforward optimization pipeline. And a funny thing about this is this work has only appeared within the last 2 years. So as you can see on the scholar, this work has been cited more than 5,000 times since the year 2023, and after 2 years on topic conferences, especially in CVPR 2025, it has formed a separate cluster of publications which has shown a new trend, a new emerging trend within computer vision and graphics community. And for this thesis, we focus on 3 stories or 3 objectives, as you can see. So the first one is we focus on the efficiency and scalability based on a frame filtering strategy we proposed. And this has led to a publication in SYCC 2024, which was Phúc Index Conference. And the second one is the post-guided 4D Gaussian splatting, where we try to integrate post and diffusion priors into the generation and reconstruction of entities within the dynamic scenes. And we have currently finished the papers, and we try to submit them onto journals. And the second one, we proposed a novel benchmark. This is GS3DORC within the Shireka competition. And this has led to the publication in the Computers and Graphics Journal, which is the Q2 journal. And so we move on with the later works.
So now let's move on to related work. We first talk about COMAP 3 3DGS. Well, about COMAP, it is a model to use the social promotion to recompute the camera modes. And in this work, they try to train the Gaussians and estimate camera modes as processing the frames sequentially without the need of COMAP module. For dynamic scene reconstruction, this is a task to reconstruct a scene that may be changed over time. And this requires to track the motions and the deformation of the objects. About neural human rendering, this is a reconstruction task again, but it is specified on human geometry and particular motion of a human. About 3D object part retrieval, this task is involved in retrieving 3D objects by just from their smaller parts instead of their whole object. The key idea is inspired by the human perception as we tend to recognize the object by their symmetry parts.
contributions. As you can see, we have 3 contributions over here, again. So to start with, we'll start with the frame filtering contributions. So traditionally in 3D Gaussian splatting, we will consider all frames within the data at once, whereas in COMAP 3D Gaussian, we will try to learn the transformation between frames and frames, so they will process sequentially, but this essentially will come to 2 issues. So first of all is the dilated effect, which means if I want to record a scene with very high fidelity, and I try to slow down in this, so what's going to happen is we have frames with overlapping scenes or frames that may be duplicated, and which may not contain extra information that we want to perform reconstruction. And the second one is if I have a very shaky hand like this. So maybe the camera rendering effect will not be very good because it will be very blurry and the image will not be of very high quality, and this essentially will damage the reconstruction quality. So we're proposing a frame filtering strategy to mitigate these effects. So to start with, we propose a frame quality scoring function based on the technograph values, which is a frame sharpness assessment. So behind the technograph, we would like to keep the image within our reconstructed data set. And to formulate this, we try to normalize the weight by using a z-score normalization. And we propose this as a distribution of technograph. So essentially, we want to randomly select top P% of frames, actually on top P%, but the top P most likely frames, because we don't want to directly choose the top frames with highest quality, because it may lead to loss of information within specific regions. So in most of our experiments, we choose P equal to 80. And we follow the traditional convention of the reconstruction task. We use the text and temples data set, and we construct it based on the 4 scenes of the data set. And in order to mimic the dilated recording process, we create separate settings, that is the duplication of frames. And for the evaluation metrics, we follow the traditional convention of Gaussian splatting proposed by the original authors. So we have the metrics for novel view synthesis, structural similarity, pixel noise ratio, perceptual similarity, and we have the camera pose estimation, which is the RPE and translation, rotation, and the ATE. And we also, in order to prove our scalability, we also measure in terms of resources usage, which include the VRAM usage and the training duration. So as you can see over here, we bolted the results of the top performed settings. Although our approach, the sample 80% one, may not appear to be very dominant, but the resource utilization can be saved in terms of virtual program and training time, while still maintaining a fairly competitive rendering effect. And on the left-hand side is the ground truth, and on the right-hand side is our rendered image. Yes. And the training camera pose are well aligned with ground truth. And here's some demos of our trained our reconstructed scenes.
Now let's move on to our next contribution, post-guided 4D Gaussian splatting for dynamic objects. So here in detail, we first have a monocular video consisting of multiple objects that move each other. And the output is the 4D Gaussian splatting to reconstruct the dynamic scene of the video. So what's wrong? So there are many works that are proposing a lot of guidance to improve the geometry and the information of the reconstruction. For example, pose guidance and diffusion guidance. But what we observe is that pose guidance with very well uploaded objects, missing some views of the parts. And diffusion guidance, they struggle to handle objects with high information. So a question pops up. Can we really orchestrate the 2 guidance without the knowledge conflict and together improve the quality of the reconstruction? What we did is to answer this question. So we first proposed a kind of coordinate system called pose-centric system. This is where the pose model centers is aligned as the origin. This allows us to capture all the angles of the pose model by just simply orbiting the camera around the origin. Next, we are able to isolate the object individually. As you can see right here, the two humans are isolated, scale, and the position are normalized. Thanks to the pose information, we are able to know the location of each object, and therefore can create a transformation, alpha transformation to be more specific. Particularly, we first project the pose model into the image, having the same dimension as the input frame from the video. Next, we project it again, but when the position is normalized. From this, we are able to create an alpha transformation, including the scale and the translation, to process the input frame into the object-centered image. Oh, okay, everything works kind of fine, but what about when the object is out of frame? We still want the scale and the position of the object to be consistent when we crop out. Thanks to the pose information again, we can estimate the general appearance of the object, although some of the parts may be missing. To further improve, we add a boundary mask and a visible filter to only allow gradient signal of the in-frame parts during the training. So from what we propose, we create a pipeline consisting of two phases. In the first phase, we take a frame from the video, extract the key point projections to create object image. We incorporate this with the pose to train the Gaussian splatting model. Notice on the right, we also supported the 3D diffusion driver through the SDS bus. In the second phase, we take the train model from the phase 1 and start to deform the pose full timestamp. Then we train the Gaussian splatting to align with this. We also use the diffusion model to improve the general appearance of the model. So here are our result in the first column. There are the references, and in the second column is from our method. And generally, our method's result have a better geometry structure and higher consistency of Gaussians. We also highlighted some of the artifacts for Incanasmall to show that some those artifacts may be produced from the baselines, but our method can mitigate. So to compare the results, we evaluate the reference field from different angles with the reference frame. The two main metrics are lift and LVIBS for semantic and perceptual evaluation. And from the statistics and the figures, it shows that our method is outstanding in almost all the configuration, and the overall table shows that we are still behind.
Okay, so the third story that we're going to tell you about is the part level understanding. So when we're trying to talk about dynamic scene understanding, we also want to understand the interactions and the parts of objects within the dynamic scene. So for this, we propose a novel benchmark, which I believe that there has been limited works on working on the part level understanding within the Gaussian splatting scope. So we propose a novel challenge where each contestant will have to retrieve relevant Gaussian parts from a complete Gaussian splatting objects. And we also propose a total view data set that we have construct. And the data set is constructed across multiple categories. We have 23 big categories and 507 small categories, and which shows a span of daily life objects within different contexts. And here are some examples of our data sets. You see we have the hammers, the airplanes, the couch, which shows that our reconstructed data set has a very has a great variety of categories among the data set. So to start off, in order to reconstruct the data sets, we have handcrafted a set of prompts, and we use Punya 3D, which is text to mesh a model. So they will generate the initial mesh with high level fidelity, and based on the mesh, we can capture the multi-view image, and we can, based on the multi-view image, we can follow the traditional 3D Gaussian splatting model to reconstruct the scenes. And after the reconstruction, we use segment ending 3D Gaussian model, which will help us to automatically segment the models into different parts, meaningful parts. And Our challenge has attracted three teams of participation, and here's the summary of their approaches. So the first team, NTK, proposed an approach based on the feature extraction of both the Curie full Gaussian model and the 3D Gaussian spline part database. So they extract the features based on value V2 and then use cosine matching. Another approach is that the team NMQ, they propose directly comparing the embeddings of the complete 3D Gaussian models with the Gaussian model of the parts using doodle clip, which is a clip model for learning features from the neural scene representation. And the third one is the team NMQ, where they propose comparing this full complete object and the parts based on the binary masking of each of the parts within the object. And the overall result shows that the team NTK actually has a higher performance, especially under the setting as 0.8, where they show superior performance over other approaches, and the NQ approaches just barely exceeds the randomization. And across the precision recall curve, you will see that the superiority of the NTK approach actually shows with the highest area under the curve. So to sum up, in this work, we propose three contributions. One is the frame filtering strategy for scalable Gaussian spline reconstruction generation. And another is the canonical closed alignment and diffusion priors to handle the occlusion of humans within the dynamic scene. And we propose the very first sparse level retrieval benchmark for 3D Gaussian spline. However, there are some limitations. First of all, the frame filtering is still using a very simple metric and may need further adaptive and online selection. And for the post-guided 4D Gaussian spline, the required post and attempt models may lead to the limiting of generality across objects. We want to generalize this solution further for more articulated objects, such as animals. And for the GS3 ORC, the approaches currently still ignoring semantics and languages understanding and have modest performance. And the data set, we want to expand further in terms of categories and in terms of scales. So to sum up, we try to advance this work towards holistic dimension understanding under the triad of semantics, efficiency, and fidelity. And they have been a great journey with us, and we hope future students will join on this journey with us. And as you can see, our work has led to two publications, which we have presented earlier. And we would like to thank you to our dearest advisor, Associate Professor Jeffrey Chip, and Associate Professor Luận for their throughout mentorship, and also their guidance for us since our day one within the academic journey. Thank you to all the lecturers and academic staff members and also all the student interns from Software Engineering Lab, CRHP in the US. And thank you all, especially all the guys over here from the class of 2020 enthusiasts. We really hope that you guys succeed in the future. Go get it, guys. And thank you to all our families and friends for the traditional love, patience, and your faith in us. And especially, personally, thank you guys for being the best teammate I could have throughout the years. So, we're now open for all the questions from the business events community. Thank you very much for your attention.
I invite Thảo to have the evaluation or ask other questions to the team.
Ladies and gentlemen, I would like to